Righto, in this screencast we're going to look at the inverse function, and before we do, we're going to identify or define the identity function, what's known as the identity function, which is simply y equals x, or function of x equals x, just maps to itself. Each point in the domain maps to the same point in the range, so we end up with a straight line y equals x. That's called the identity function. All right, we'll come back to the significance of that in a moment. Now let's move into the inverse function. Right, so the inverse function, we're going to cover all these aspects of the inverse function, but I'm going to start off with a fairly simple definition of an inverse function. Now, that's firstly, not all functions have inverses, and we'll go into, and we have already in a previous screencast looked at the one-to-one nature of functions and therefore whether they have inverses. I'll come back to that. But the inverse function is defined as each ordered pair does an XY switch. So in creating an inverse function, each ordered pair does an XY switch. So an XY, each point does an XY switch. So for instance, if I've got let's have a look at just a simple say straight line, y equals 2x, goes through the origin, y equals 2x. If I wanted to create the inverse function to this, what I would do is I'd look at each ordered pair and I'd do a coordinate switch. So 0, 0, that's not going to take much. When we go to 1, 2, which is that point there, 1, 2, when you put x equals 1, you get y equals 2. I'm going to switch the coordinates so that on the inverse I've got 2, 1. So that point there, 1, 2, maps to the point here, 2, 1. And if I keep doing that, I go to 2, 4. I go to 2, 4 here. Then I get a point over here, 4, 2, that's on the inverse of y equals 2x. So what I'm doing is I'm looking for the inverse of the function y equals 2x. So every function possibly has an inverse. And in order to find that inverse, we could just do, I've now got 3 points, 0, 0, 2, 1, 4, 2, do a coordinate switch. I join those 3 points up, and I didn't really do a very good job of that, but this here would be the inverse of the function y equals 2x, and we'll talk about actually in a moment what that function is. Well, let's talk about it now. So what do you think it is? Well, this is 2x, so y is twice x. In this case, if y is twice x and we do a coordinate switch, see on the line here, x is now twice y, so we have the function y equals 1/2 x, don't we? So these are inverses of each other. Now let's have a little explore of what that means. Firstly, while we've got the two graphs up, it would make sense to acknowledge the symmetrical nature around y equals x. And if you have a look there, the red line is reflected in y equals x to create the green line. So inverses are reflections of each other in y equals x. Inverses are reflections of each other in the line y equals x. So that's something, that's the graphical property there. Talked about the domain range switch. So what we have now for each of our x coordinates here on the red line become our y coordinates here on the green line. So what in effect happens is our domain of our red becomes our range of our green, and the range of our red becomes the domain of our green. So that's our domain range switch. There I go, I've hit that button again. What we find here also is that if we look at the composition function of these two, so if I call, let's say f of x is 2x, which is my original function, and g of x equals the inverse, which is 1/2 x. If I look at the composition, so if I look at f of gx and see what I get there, then I get f of 1/2 x. Let's evaluate this. What function do I get? F of 1/2 x, which is 2 by 1/2 x, or which equals x being the identity function. Let's just check what happens when we take the composite of g of f. I get g of fx, so I get g of 2x, which equals, what does this mean, a half by 2x, which equals x. So I end up with the identity function. So we can define our inverse function as being two functions, they're inverses of each other if their composition results in the identity function. So let's just write that out. Two functions are inverses of each other if their composition results in pause a moment. Okay, so just going back into this definition. So the two functions are inverses of each other if their composition results in the identity function as seen here. So 2x and a half x, we've already identified that they are inverses of each other through our xy switch here, and taking the compositions results in the identity function. So that's a feature of identity functions. There's loads going on here. So that's the compositions result in the identity. Now we'll look at two other things. We'll look at how to find the inverse function in an algebraic sense, and also then how to check whether functions are actually invertible. But so far, just to summarize, two functions are the inverses of each other if they're reflected in y equals x, and if their composition results in the identity function. Okay, how to find an inverse function. So how to find the inverse function should it exist. Should it exist, the inverse function. Okay, so let's take a function, e.g. find the inverse of, let's say, y equals 2x minus 1, or this might be in function notation here, it's probably more likely, so that's fx equals 2x minus 1. Find the inverse of function x equals 2x minus 1. Okay, so the first step here is to write it actually as, what should I write in green? Write it as y equals 2x minus 1. Okay, so write as y equals. Okay, so that's step one. Step two is do an xy switch. So change y to x and change x to y. So that is affect an x y switch. So we do that. So this is down the left column of the actions, down the right column we're carrying out the instructions. So make it y equals and then switch x and y around. That's our domain range switch. Back to what we talked about up here. Every point here changing x, y. It's an x, y switch in every ordered pair on my function. Now I'm trying to find the inverse function. That's how we do it. So here's algebraically what it looks like. Affect an x, y switch. The next step is to then make y the subject. So it's a nice little algebraic move here. So now make y the subject. 2y equals x plus 1. So y is equal to x plus 1 over 2. So what we found when we made y the subject, this is now the inverse function. So the last step is to write in f minus 1x notation, which is therefore f minus 1x equals x plus 1 over 2. Now f minus 1x here is the notation for the inverse of f of x, f minus 1x. Okay, so that's how to algebraically go about it. They're the steps. Fabulous. The last thing to talk about is is it invertible? Is the function invertible? Does it have an inverse? The answer to that is yes, if it's a one-to-one function. So is it one-to-one? Is it one-to-one? If the answer is yes, if it's a yes, then it oh dear, it is invertible, or it does have an inverse. If the answer is no, then it is not invertible. And this one-to-one, how do we test for one-to-one? We test for one-to-one with the horizontal line test, don't we? The horizontal line test. Okay, so the horizontal line test, so if it's a, let's say it's y equals x squared plus 1, then we have a look at that function, we have a look at the graph of it, and we see is it one-to-one? The answer is no, it is not one-to-one. So it's not one-to-one. So as a function x squared plus 1, it's not invertible. However, if we restrict the domain, by restricting the domain, so what we can do is we can restrict the domain to either x is greater than or equal to 0, or x is less than or equal to 0 at the turning point. By restricting the domain, we find an invertible function. So if we restrict this now to just, say, this section here, so we just define this function for x is greater than or equal to 0, now we've restricted the domain, and now it is invertible because it is one-to-one, and we can go ahead and find its inverse. Okay, that's all for this lesson. I hope you've enjoyed it as much as I have enjoyed giving it. I'll see you in class in the next few hours. Cheers.